PKCE Flow Phase 1 Initialization and Authorization Request. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. The PKCE flow, pronounced PKCE, which stands for Proof Key for Code Exchange, begins when a user wants to authenticate with an application. This first phase covers the initialization steps that the client application, meaning the application the user is trying to access, for example, a mobile banking app or web application, must perform. It also covers constructing the authorization request that will be sent to the authorization server, which is the identity provider, for example, Google or Microsoft, that verifies who the user is. The flow starts with the user initiating a login action. This could be clicking a sign-in button in the application or trying to access a protected resource that requires authentication. At this moment, the client application, that is the app the user wants to use, springs into action to prepare for the secure authentication process. The first critical step is generating the code verifier. This is a cryptographically random string that serves as a secret known only to the client application, the application the user is accessing. The specification requires this string to be between 43 and 128 characters long, and composed only of unreserved URI characters. These are URL-safe characters, which include uppercase letters, lowercase letters, digits, hyphen, period, underscore, and tilde. The client typically generates this by creating 32 random bytes using a cryptographically secure random number generator. It then uses base 64 URL encoding on those bytes. This is a way of converting binary data into text that can safely be transmitted in URLs, producing exactly 43 characters with sufficient entropy, meaning enough randomness, to be unguessable. Once the code verifier is generated, the client, meaning the app the user wants to access, must store it securely because it will be needed later in the flow. On mobile applications, this means storing it in the system keychain on iOS or the key store on Android, which are secure storage areas provided by the operating system. For web applications, it might be stored in secure server-side session storage. For single-page applications, meaning JavaScript apps that run in the browser, storing it in memory is the most secure option to prevent cross-site scripting attacks, also called XSS attacks, from accessing it. Next, the client computes the code challenge from the code verifier. This is done by taking the SHA-256 hash of the code verifier. SHA-256 is a cryptographic hash function, which is a mathematical algorithm that takes an input of any length and produces a fixed 256-bit output. The key property of SHA-256 that makes PKCE work is that it's a one-way function. This means you cannot determine the input from the output, nor can you work backwards from the hash to figure out the original code verifier. After computing the SHA-256 hash, the resulting 32 bytes are base 64 URL encoded to produce the code challenge string. The client then constructs the authorization request URL. This URL points to the authorization server's authorization endpoint, which is the web address where authentication requests are sent, and includes several query parameters, which are pieces of information added to the URL. The response type parameter is set to code to indicate we're using the authorization code flow, which is the most secure way to handle authentication. The client ID parameter identifies which application is making the request. It's like a username for the app. The redirect URI specifies where the authorization server should send the response, meaning where to send the user back after they log in. The scope parameter defines what permissions are being requested, like access to read email or view profile information, and for OpenID Connect, which is the identity layer we're using, this must include OpenID. The state parameter is a random value used for CSRF protection, which stands for cross-site request forgery protection, preventing attackers from tricking users into making unwanted requests. The two PKCE specific parameters are code challenge and code challenge method. The code challenge parameter contains the base 64 URL encoded SHA-256 hash of the code verifier that we computed. This is essentially the scrambled version of our secret that cannot be unscrambled. The code challenge method parameter should be set to S256 to indicate that SHA-256 hashing was used to generate the challenge from the verifier. S256 stands for SHA-256. This distinguishes it from the plain method, which should never be used. The plain method provides no security benefit because it does not scramble the code verifier at all. After constructing this authorization URL with all the required parameters, the client redirects the user's browser to this URL, meaning it sends the user to the authorization server's login page. On mobile applications, this is typically done using the system's secure browser component like AS Web Authentication Session on iOS or Chrome Custom Tabs on Android, which are special browser windows provided by the operating system. For web applications, it's a standard HTTP redirect, meaning the server tells the browser to go to a different page. For single-page applications, meaning JavaScript apps running in the browser, it might be a JavaScript-initiated redirect that changes the browser's location. This redirect takes the user away from the client application, the application they were trying to use, and to the authorization server, the identity provider. The user is now interacting directly with the authorization server, which is typically a trusted identity provider like Google or Microsoft. The authorization server receives the request with all the parameters, including the code challenge. The server validates the parameters, which means it checks that everything is correct. It ensures the client ID is valid and the redirect URI matches a registered value for that client, and then prepares to authenticate the user. PKCE Flow Phase 2. User Authentication and Consent. In this second phase, the user interacts directly with the authorization server, which is the identity provider, such as Google or Microsoft. Their purpose is to prove their identity and grant permissions to the client application, meaning the application they are trying to access. This is a critical security boundary where the user must authenticate themselves, or prove who they are, and make an informed decision about granting access to their resources. When the authorization server receives the authorization request from the client, it first validates all the parameters, verifying that everything is correct and makes sense. It checks that the client ID corresponds to a registered application, confirming that this application is known and allowed to use the authorization server. It verifies that the redirect URI exactly matches one of the URIs, that is, web addresses, registered for this client during the application registration process. This exact matching is crucial for security because it prevents attackers from redirecting the authorization response to a malicious endpoint they control, which means preventing the login result from being sent to a bad actor's server instead of the real application. The authorization server also validates the PKCE specific parameters. It checks that the code challenge is present and properly formatted, meaning it's there and looks correct. It verifies that the code challenge method is either S256 or plain, though servers following security best practices should reject the plain method because it's not secure. The server validates that the code challenge string is the correct length and contains only valid base 64 URL characters, which are the safe characters that can be used in web addresses. If any of these validations fail, the authorization server typically displays an error page rather than redirecting back to the client, since it cannot trust the redirect URI if the client ID is invalid. After validating the request parameters, the authorization server presents a login interface to the user. This is where the user must prove their identity. The authentication method depends on the authorization server's configuration and the organization's security policies. The most common method is username and password, where the user enters their credentials into a form. However, modern systems increasingly use stronger authentication methods. Multi-factor authentication, also called MFA or 2FA, which stands for two-factor authentication, is becoming standard for sensitive applications. After the user enters their password, the server might require a second factor, meaning a second way to prove it's really you. This could be a code from an authenticator app like Google Authenticator, a code sent via SMS text message, a push notification to a registered mobile device asking you to approve the login, or a biometric factor like a fingerprint or face recognition. Some organizations use hardware security keys that implement standards like FIDO2 or WebAuthn. These are physical USB devices or wireless keys that provide strong phishing-resistant authentication, meaning they can't be tricked by fake websites. The authorization server might also have session management capabilities. If the user has recently authenticated to the authorization server for another application, meaning they already logged in a few minutes ago for a different application, they might already have an active session. In this case, the server can recognize the user from their session cookie, which is a small piece of data stored in the browser that remembers you are logged in, and might skip the authentication step entirely. Alternatively, the server might require re-authentication depending on security policies, the sensitivity of the requested scopes, meaning permissions, or how much time has passed since the last authentication. After successful authentication, the authorization server presents a consent screen to the user. This screen is a crucial security and privacy feature. It shows the user which application is requesting access, typically displaying the application's name, logo, and description. More importantly, it shows exactly what permissions or scopes, meaning what the app wants to be able to do, the application is requesting. These are presented in user-friendly language rather than technical scope names. For example, instead of showing read contacts, it might say read your contact list. The consent screen allows the user to make an informed decision about whether to grant the requested permissions. The user can see exactly what the application will be able to do on their behalf. Some authorization servers allow users to modify the requested permissions, granting only a subset of what the application requested. The user can choose to approve the request, granting the permissions, or deny the request, refusing to give the application access. If the user clicks deny or cancel, the authorization server redirects back to the client's redirect_URI, meaning it sends them back to the application, with an error parameter set to access_denied. The user is then returned to the client application, which should handle this gracefully by informing the user that access was not granted and potentially allowing them to try again or continue without authentication. When the user clicks approve on the consent screen, the authorization server processes this consent decision. It records that the user has consented to these specific scopes for this client application, meaning it saves that the user has given permission. This consent might be stored for future authentication attempts, potentially allowing the user to skip the consent screen on subsequent logins if nothing has changed. The server then generates an authorization code, which is a short-lived, one-time use token. This is a temporary code that represents the user's consent and authentication. Here's where PKCE comes into play on the server side. The authorization server must store the code challenge that was provided in the authorization request and associated with this authorization code, linking them together. This binding is typically stored in a fast key value store, such as Redis or Memcached. These are specialized database systems for quick lookups. The authorization code is used as the key, similar to an index in a filing system. The stored data includes the code challenge, the client ID, the redirect URI, the granted scopes, the user identifier, and an expiration timestamp. This association is critical for the security of PKCE because it allows the server to verify later that the token request is coming from the same client, specifically the same app, that initiated the authorization request. The authorization code itself is a random, unguessable string. It is typically much shorter than the code challenge, perhaps 30 to 40 characters. The code has a very short lifetime, usually between 1 and 10 minutes. This short lifetime limits the window during which an intercepted code could potentially be exploited. This means that if it is stolen, An attacker has only a few minutes to try and use it. The code is also designed to be single-use only. This means that once it has been exchanged for tokens, it becomes invalid and cannot be used again. PKCE Flow. Phase 3. Authorization Code Delivery and Token Request. The third phase of the PKCE flow involves delivering the authorization code back to the client application, and the client then makes a token exchange request. This is where PKCE's security mechanism becomes most apparent, as the client must prove it is the same application that initiated the flow by providing the code verifier. After the user has successfully authenticated and consented, and the authorization server has generated and stored the authorization code with its associated code challenge, the server needs to return this code to the client application. This is done through an HTTP redirect. The authorization server constructs a redirect URL using the redirect URI that was provided in the authorization request. It adds the authorization code as a query parameter named code. It also includes the state parameter that the client provided in the original request, allowing the client to verify this is a legitimate response to a request it initiated. The redirect URL looks something like https://clientapp.example.com/callback?code AUTH_CODE_VALUE and sign state STATE_VALUE. The authorization server sends an HTTP 302 redirect response to the user's browser, pointing to this URL. The browser automatically follows the redirect, making a GET request to the client application's callback endpoint with the authorization code included in the URL. This means the authorization code briefly appears in the browser's address bar and will be recorded in the browser's history. This is not a security problem in the PKCE flow because the code alone is useless without the code verifier. An attacker who sees the code in the address bar or retrieves it from browser history cannot use it to obtain tokens because they don't possess the secret code verifier that only the legitimate client application has. When the client application receives the callback request with the authorization code, it must perform several validation steps before proceeding. First and most importantly, it must validate the state parameter. The client extracts the state value from the query parameters. It then compares this value to the state value it generated and stored before initiating the authorization request. If these values don't match exactly, the client must reject the response and treat it as a potential cross-site request forgery attack. The state validation ensures that this response corresponds to an authorization request that the client actually initiated. After validating the state, the client extracts the authorization code from the query parameters. It also retrieves the code verifier that it generated at the very beginning of the flow and has been storing securely. Now comes the critical moment. The client must make a token exchange request to convert the authorization code into actual tokens. The token exchange request is an HTTP POST request made directly from the client to the authorization server's token endpoint. This is a server-to-server or back-channel request, meaning it doesn't go through the user's browser. For web applications running on a server, this is a standard HTTP request. For mobile applications, this is a direct HTTP request from the app. For single-page applications, this is typically a fetch or XML HTTP request call, though it requires proper CORS configuration on the authorization server. The token request includes several parameters in the HTTP POST body, using the application/xwww form URL encoded content type. The grant type parameter is set to authorization code to indicate we are exchanging an authorization code for tokens. The code parameter contains the authorization code that was just received. The client ID parameter identifies the client, just as in the authorization request. The redirect URI parameter must be included and must exactly match the redirect URI from the authorization request. This is another security check by the server. The most critical parameter for PKCE is code verifier. This parameter contains the original random string that the client generated at the very beginning of the flow, before computing the code challenge. This is the secret value that only the legitimate client possesses. Remember, what was sent to the authorization server in the authorization request was the code challenge, which is the SHA-256 hash of this verifier. Now, the client is revealing the original verifier to prove its identity. The authorization server receives this token request and begins its validation process. It first extracts the authorization code from the request and looks it up in its storage to retrieve the associated metadata. This metadata includes the code challenge that was stored during the authorization request, along with the client ID, redirect URI, granted scopes, and user identifier. If the authorization code is not found in storage, it might have expired or already been used, and the server rejects the request with an invalid grant error. The server validates that the authorization code hasn't expired by checking the stored expiration timestamp. It validates that the client ID in the token request matches the client ID associated with the authorization code. It validates that the redirect URI in the token request exactly matches the redirect URI that was used in the authorization request. All of these checks ensure that the token request is coming from the same client that received the authorization code. Now comes the PKCE verification. The authorization server takes the code verifier from the token request and performs the same transformation that the client performed initially. It computes the SHA-256 hash of the code verifier and base64 URL encodes the result. It then compares this computed value to the code challenge that it stored when it issued the authorization code. If these values match exactly, the verification succeeds. This proves that the client making the token request possesses the original code verifier and is therefore the same client that initiated the authorization request. If the values don't match, the server immediately rejects the request with an invalid grant error, as this indicates either an implementation bug or a potential security attack. PKCE flow. Token response and secure access. The final phase of the PKCE flow involves the authorization server issuing tokens after successful verification, and the client using these tokens to establish an authenticated session and access protected resources. This phase completes the authentication flow and enables the client application to operate on behalf of the authenticated user. After the authorization server has successfully verified the code verifier matches the stored code challenge and all other validation checks have passed, it proceeds to issue tokens. Before doing so, it marks the authorization code as used in its storage system. This is a critical security measure that prevents the authorization code from being used again. If another request comes in trying to use the same authorization code, the server will reject it with an invalid grant error. Many authorization servers go further and implement authorization code replay detection. If they detect an attempt to reuse a code, they not only reject the request but also revoke any tokens that were previously issued using that code. This helps detect and mitigate attacks where an authorization code might have been intercepted. The authorization server constructs a token response, which is a JSON object containing several important components. The response includes an access token, which is the credential that the client will use to access protected resources on behalf of the user. The access token can be in various formats. It might be a JWT with embedded claims, or it might be an opaque random string that the resource server must validate by calling back to the authorization server. Access tokens have limited lifetimes, typically ranging from 1 hour to 24 hours depending on security requirements. The response also includes an ID token, which is specific to OpenID Connect and provides information about the authentication event and the user's identity. The ID token is always a JWT, which consists of 3 parts separated by dots: a header describing the token format and signing algorithm, a payload containing claims about the user and the authentication, and a signature that proves the token was issued by the authorization server and has not been tampered with. The ID token includes standard claims like sub for the subject, a unique identifier for the user, ISS for the issuer, the authorization server's identifier, AUD for the audience, the client ID this token is intended for, express for expiration time, and IAT for issued at time. It may also include additional claims about the user like their name, email address, and other profile information depending on the requested scopes. The token response includes a token underscore type parameter, which is almost always bearer, indicating that these are bearer tokens that can be used by whoever possesses them. The expires underscore in parameter tells the client how many seconds until the access token expires, allowing the client to know when it needs to refresh the token. If the client requested the offline underscore access scope and the authorization server supports it, the response will also include a refresh underscore token, which is a long-lived credential that the client can use to obtain new access tokens after the current one expires without requiring the user to authenticate again. The authorization server sends this token response back to the client as a JSON object in the HTTP response body with a 200 OK status code. The client receives this response and must validate it before trusting the tokens. For the ID token, the client must perform several critical validations. It must verify the signature using the authorization server's public key, which is typically obtained from the server's JWKS JSON web key set endpoint. It must verify that the issuer claim matches the expected authorization server. It must verify that the audience claim matches the client's own client ID. It must verify that the token has not expired by checking the expiration claim against the current time. If the client included a nonce parameter in the authorization request, which is recommended for additional security, it must verify that the nonce claim in the ID token matches the nonce it sent. After all these validations pass, the client can trust the ID token and extract the user's identity information from it. The subject claim provides a stable identifier for the user that the client can use to look up or create a user account in its own database. The client can extract profile information from the token's claims to personalize the user experience. The client has now successfully authenticated the user and can establish an authenticated session in its own application. The client stores the access token securely because it will need this token to make API requests to resource servers on behalf of the user. On mobile applications, tokens should be stored in the system keychain or keystore with appropriate security attributes. For web applications, tokens might be stored in secure server-side session storage. For single-page applications, tokens can be stored in memory. This is most secure, but they are lost on page refresh. Tokens can also be stored in session storage, which persists across page refreshes but not browser sessions, or as HTTP-only secure cookies if the architecture supports it. The client should never store tokens in local storage due to XSS vulnerabilities. If a refresh token was issued, the client must store it with even greater security than the access token because the refresh token is more powerful and longer lived. The refresh token allows obtaining new access tokens without user interaction, so its compromise would give an attacker long-term access to the user's resources. On mobile platforms, refresh tokens should be stored in the keychain or keystore with the highest security level available, potentially requiring device unlock for access. With the access token in hand, the client can now make requests to resource servers, APIs, to access protected resources on behalf of the user. These requests include the access token in the HTTP authorization header using the bearer authentication scheme. The header looks like authorization bearer access underscore token underscore value. The resource server receives this request, extracts the access token from the header, and validates it. This validation might involve verifying a JWT signature and checking its claims, or it might involve calling the authorization server's introspection endpoint to validate an opaque token. If the token is valid and has the required scopes for the requested resource, the resource server processes the request and returns the protected resource. When the access token eventually expires, the client checks if it has a refresh token. If it does, the client makes a refresh token request to the authorization server's token endpoint with grant type set to refresh token and including the refresh token. The authorization server validates the refresh token and issues a new access token, and possibly a new refresh token if it implements refresh token rotation. This allows the client to maintain access without requiring the user to authenticate again. The entire PKCE flow is complete, and the client has achieved secure authentication with protection against authorization code interception attacks. Thank you for your attendance. Please consider subscribing to the channel.